So just a reminder for everyone, we are going to create also a topic in our forum with respect to this discussion that we have today. And so I asked CLA if he wants to upload later on his slides and put a link in the forum topic on this course so that everyone can take a look at the slides and maybe the papers, a few more references that we will discuss today. Okay. So thank you all for joining. Let's start with this great new reading group session from ContinualAI. The main speakers will be CLA Liu and Chensen Wu. And they will talk about their recent, I would say, amazing paper, Generative Feature Replay for Class-Incremental Learning. This paper, I think it was submitted and accepted to the CL Vision workshop at CVPR. And they will talk about this. Please keep your question maybe till the end of this session, and then we can open a discussion and ask the others some questions. So thank you again for joining. Remember that this is part of a series of reading group sessions that we are holding every Friday. So you can join them, and of course you are free also and welcome to make a donation to ContinualAI to support these kind of events and all the things that we are doing in this nonprofit research organization. So thank you again, and CLA, please go ahead with the presentation.
Okay, can you see the screen?
Yes, we can see it.
Okay, great.
And thank you so much for being here, by the way.
Hello, everyone. My name is Xiaolei, and I'm gonna present our recent work together with Chensen. Thanks for having me here. Currently, I work in Computer Vision Center at Autonomous University of Barcelona. And let's start. So this is a figure from a recent continual learning theory paper. And they divide the continual learning method into three main categories: replay-based, regularization-based, and parameter isolation-based method. So obviously, our generative feature replay belongs to a replay-based method. It's actually a pseudo-rehearsal method according to this theory. And in our group, we have been working on continual learning for quite some time. Here I list some of publications from our group. We have more or less covered all three different categories. For instance, in rotational networks, which is the improved version of EWC, in memory replay GANs, we first proposed to use the conditional GAN as a replay method. In our recent semantic drift composition, we proposed to estimate drift instead of preventing the drift in the first place. And I have been also working on other applications like object detection. One of our group members also worked with ternary feature mask, which is one of the parameter isolation based method. Today we are gonna focus on the last one, the generative feature replay for class-incremental learning. And feel free to check out these papers if you are interested in. And also, if you want to follow the latest papers about continual learning, welcome to visit our GitHub GitHub page, Awesome Incremental Learning. And to talk about the rehearsal-based method here, I list some related works. Because in the survey paper I mentioned before, they are working on, we call it TaskAware incremental learning. So when you do inference, you know which task it belongs to. So in our case, we are dealing with the class incremental learning, which like in the inference time, we don't know which task it belongs to. So in this category, there are actually three subcategories. The first one is exemplars based. So the idea is very simple to keep like a small amount of data from previous task, right? So for example, in ICAR, they propose to use a way to select which exemplars to keep. They call it herding, and they also use nearest mean classifier as the evaluation method. And some other papers like BIC, they propose bias correction layer. That's important because when we keep a small amount of data, we have suffered from unbalanced problem. That's why this is important. Also in Lucy, they kind of dealing with the same unbalanced problem. In second category, image generation based method, I think the deep generative replay is the first to propose to use GANs to help with the continual learning. And then in the next year, in our group, we propose memory replay GANs. We use the conditional GANs instead of normal GANs. We see some advantages using these conditional GANs. And later on, there are some follow-ups. We can see I list here. And the last category is the feature-based generation. One of the very first one is the FairNet. They propose to use an encoder and decoder to replay with mean and covariance for each class. Later on, like recently, there are also some method based on feature maps replay and also latent features replay. So we are more or less in the same category. So here a bit of discussions about 3 subcategories. For example, in exemplars-based method, we know it's kind of straightforward. However, sometimes there might be the private issue. Then in that case, you cannot keep exemplars. Also, like it's always suffer from unbalanced problem, right? You have a small amount of data from per task, then you cannot learn it very well. And also for some large data sets, you have to spend quite some memory to store these exemplars. For image generation part, it's also kind of straightforward as long as you can generate realistic or high resolution images, then you are good. However, in practice, it's still a quite hard problem to generate these synthetic images. Even like in some papers, they claim they can generate better quality images. However, the models and also the training procedure could be so complex that it's not so easy to use for continual learning. And for feature generation, the good thing is it's very easy to generate. However, we have to deal with the drift happening in the lower level of feature extractors. So here in the figures on the left side, it's a figure showing generative image replay, where we can see we can train a generator to generate the images from previous tasks. Then we can join with current data. Then we train a new model together. That works good if you can generate good images. And on the right side, it's generative feature replay. What we proposed in the paper, we instead of generating images, we generate features on the top of feature extractor. At that point, the features kind of easy to generate. However, the feature extractors could move around, and we might forget what we have learned before. So here we add additional loss function in blue, which is the distillation loss to try to avoid the drift in the feature extractor. And we also did some forgetting analysis using the canonical correlation analysis. And here you can see for fine-tuning, here we assume we have 4 tasks in CIFAR-100. and the horizontal axis is the different blocks of networks, and the vertical axis is after training each task, we want to compare the correlation relationship between different models. If you see only the top block, we can see here after training the first task, we compare it with itself. It's all 1 in yellow. And after training the second task, we can see the correlation is getting lower because when we do fine tuning, we kind of change the parameters in the network. So while we are training for more tasks, actually the correlation is going decreasing. So by seeing this, we can see the forgetting happening during the training. And we also did this for learning without forgetting, generative image replay, and also the feature distillation. As we can see for feature distillation, it's already better than some of other methods. And then we combine the feature distillation and generative feature replay. We can see we get very yellowish figures, which means the correlation between different models after training for task, it's still kind of well aligned. And then the Chen will present the detailed method.
Great. So thanks, CLA. And I think you have to exit from the presentation and then.
Yes. Okay. Yeah.
Now Chen-san can present now.
Okay, can you hear me and see the screen?
Yes.
Yes.
Yeah. Okay. Okay, I'm Chen, and I'm going to present the method in detail. So here it shows how it works, how it's trying to learn the task T+1 after learning the task T, and prevent the forgetting of the previous tasks. So basically, we have H is our classifier, and F is the feature extractor, and G is our generator. Basically, when we want to learn the new task, we initialize our feature extractor and classifier and generator from the previous model. And for classifier, we trained with the cross entropy loss, and there's 2 parts. One comes from the new data set that we are going to learn, and another part comes from the previous data set, and we use the generated feature from the generator trained from the previous steps. And for the feature extractor, it's updated from the backpropagation of the classifier, and it's also updated by there's a distillation loss to keep it from drifting from the previous feature extractor. And we start from a simple model. We generate the feature by a Gaussian distribution. So basically, for each class, we approximate distribution by a Gaussian distribution. We compute the mean and variance matrix for the features, and we save these parameters, and we can generate the distribution. The benefit it's very easy, and there's no forgetting because we can fix the parameter. And to generate a more complex distribution, we propose to use conditional gap. And we notice that this conditional gap is also learned incrementally as our classifier learned incrementally. So to prevent this generator itself from forgetting, we use the method that we proposed in 2008. It's called Mergan replay alignment. Basically, the idea is we try to align the input and output of the previous generator and the new generator. So when we have the same input noise and input label, we want the output to be the same. So we align the output by an L2 loss. So here's the algorithm. Basically, we have a data set from D1 to DT. We have feature extractor, classifier, and generator. In the first task, we train the feature extractor and the classifier with the data set first. And then we fix the feature extractor. And we use the output of the feature extractor as the input to train the generator. And from the second task, it's also we first train the feature extractor and the classifier. One part from the new data set and another part from the output of the generator. The generator can generate the feature for all the previously learned classes. And then we update the new generator. The new generator is for the new data. The new generator is trained with a GAN loss, but for the previous class, it is updated without the GAN loss, but only the L2 loss compared with the previous generator. Okay, now I'm going to show the result of the experiment. We start from the ImageNet 100, which means we select randomly 100 classes from the full version of the ImageNet. In the upper three figures, it shows the average accuracy of all the learned learned classes after we learn each task. And in the lower bottom three images, we show the forgetting. There are three settings. All of them are basically we divide. We take the first half of the data set as a first task, and then we divide the remaining classes into 5 or 10 or 25 tasks. And the red curve is ours. You can see that it outperforms all the other method. And the magenta one is also ours, but with a Gaussian distribution. You see that it's also quite high compared with others. And in this figure, all the curve with markers means they don't use exemplars like learning without forgetting, EWC, and our method. And the method without marker means they need exemplars to make it work, like ICAR and rebalancing, which is the learn a unified classifier via rebalancing. So we notice that actually we have a more restrict setting than the ICAR or rebalancing because we have no exemplar. We don't have the privacy issue, and we need less memory, which we will show it later. And in the full ImageNet setting, we see that our method is also the best, and we didn't run this setting for all the other methods. We only run the method that are relatively competitive. And this is one for the CIFAR-100. We see that in most cases our method is the best, but except for the 25 task setting. And also we have we see that we outperform the method that without exemplar by a wide margin. Okay, in this slide, I'm showing the memory usage compared with our method to other methods that are using exemplars. So for example, a ResNet 18 that we are using as our feature extractor takes about 45 megabyte. And our generator and discriminator are very small because we are using a very simple model with only one hidden layer, and it takes only about less than 5 megabyte. And if you use exemplar for CIFAR, the memory usage is relatively smaller. It's comparative to the network. But when you move to ImageNet, especially to the full version of ImageNet, the memory usage is much higher than the network. Yeah, and in this page, I'm showing how the drifting of our generated feature. The red dot represent the real feature, and the blue one represent the generated feature. You see that they are quite stay together. Yeah, in conclusion, yeah, we present a new method that combines generative feature replay and feature distillation, and it works quite well. And we also noted that it's computational very efficient. We have a very small generator, but it works in very realistic data set like ImageNet. And we outperforms the other method, especially without exemplars by a large margin. Yeah, thank you for your attention. And we have our code.
Great. Thank you so much, guys.
You're welcome.
To the other joining the event, do you have some questions for our authors here?
Davide, I have a question. First, thank you for the interesting presentation. Very clear and very interesting. My question is, I read with interest the paper, and since we are doing similar things by using ContinualAI and another architecture, we also have some experience in generating features. So I read in your paper that you obtained the best accuracy by using a feature extractor up to the last level. So you generate actual feature at the last level. Whereas when you try to generate feature at lower level, you have some problems. If you can comment on this.
Right. So the question is basically like you want to generate some features from lower level features, right? Yeah, actually, indeed, we tried some architectures to generate the features in the lower levels. However, like in general, the lower features normally have like spatial information. Also, like you have a large number of feature maps. So we have tried many things, but in the end, we couldn't make it work to generate that features. Yeah, maybe I don't know if that's what you were asking.
Yeah, exactly. It was exactly this about the difficulty of generating feature at lower level, where you have, of course, 2D feature maps, and
right.
We are also having some problem, but with some progress. Maybe Gabriele and Lorenzo, which are attending to your talk, maybe you can share with you some experience on this.
Yeah, that would be great, because in the end, actually, somehow we want to generate lower level features, because in that case, then you can train more features like upper, beyond your generated features. That could be better, but if we cannot generate good features, then it doesn't work well right now.
I agree. I think it is still an unsolved problem.
Yeah, right.
So I have a couple of questions, maybe. So first of all, I was thinking to ask, why did you use like GANs instead of, for example, variational encoders or other maybe simpler generative methods, apart from, of course, what you propose with the Gaussian methods? And then, I mean, using this GAN model that you propose for generating features, what's your current like running time for your experiments at the moment? For example, on ImageNet. I mean, it's heavy to update at every time step the generative model to produce these features. Yeah.
Yeah, I think right now, like for each task, we need to kind of retrain our generator. But our generator is relatively small, as Chen Chen showed before. So I think it's still like quite fast to train the generator, because it's just 1 or 2 layers, fully connected layers. I guess it also could work with like other generative models. We have tried to use the simple version of using mean and covariance. It works. However, we have seen like it gives worse results compared to our conditional GANs. So we haven't tried like I think we also tried some other generative models, and in that we picked this one. I think it gives the best performance.
Okay, thanks. Another question, maybe, did you try to, I mean, I wanted to understand maybe better the impact of these distillation losses used for the feature extractor. So the idea, if I understood it correctly, is that you want to update your feature extractor because it may be like useful to do so, even though you start from a pre-trained model, right? For ImageNet.
Right.
But did you try to not update it at all, like keeping the feature extractor frozen and using that to extract the features and see, using maybe some examples, retain at that level, how that would perform. To say, okay, it is useful to have an additional distillation loss and to keep improving our feature extractor. Right.
Yeah, I think this is a very interesting question. We have seen like some other papers, they are directly using the pre-trained model, then they track the features, then they do some replay, right? In general, it works. But like in continual learning, at some point, we would like to update the feature extractors in the end. Then if you keep the feature extractor, I would say it could still like provide you decent performance. Then you have problem like going forward, having like more and more tasks, right? We didn't have results in the paper, but having the freezing feature extractor, it also works very good. And the main thing in our paper maybe it's like when we have a relative good feature extractor, then with our like continual learned generator, we can indeed generate very good features, even we learn it incrementally. Yeah, I don't know if Chen Chen want to comment about this question or.
Yeah, because I mean, I think that it's very interesting, especially if you can prove that, at least because I understood your idea that if you want to learn continuously, you want also to update a feature extractor. But in terms of practical applications, it would have been nice to show also that you need that distillation loss, because you can go better than just freezing the feature extractor. Just wanted to understand if you had tried that, and you had this additional insight that you could share with us.
Yeah, basically, like right now, our framework is quite like depends on how good is your feature extractor. For example, right now in our setting, we start from a relative like larger amount of classes in the first task, and we indeed we tried some starting with for example 10 classes or even smaller number of classes at the beginning. Then it's not working so well in that case, because your feature extractor is it's hard generalized to all the other classes, and during this process it's kind of difficult. So this is actually one thing we are trying to maybe tackle it in the future.
Yeah, thanks. Does anyone else have a question for our authors?
Yeah, I have a question about how do you combine the generated features and the feature extracted by your feature extractor. Do you combine them at the mini batch level, or do you have some mini batches containing only generated features and some mini batches containing only real features?
Yeah, I think correct me if I'm wrong, Chen.
Yeah.
So I think what we did is we have we combined in the mini batches, and we normally have like half batches from the current data and half batches from the generated features, right? So of course, it's unbalanced, so we add a coefficient for the generated features in order to keep balance all the classes.
Okay, so you don't have mini batches that contain some generated features and some real feature in the same mini batch. I'm right?
Yeah, it's separated. Yeah.
Okay.
Yeah,
okay,
it's separated, but you update the network together, like with the real and synthetic features.
Okay, thank you.
Yeah, I would have another one. Because you use a GAN, and you obviously also have some experience with how to use that in continual learning, is it at all hard to train that part correctly? Or because I don't know how far GANs are these days, but there's this whole problem of like mode collapse, and sometimes they just don't train well. Because I'm asking because in a continual setting, of course, you want to have something that is very robust in that sense, right? That doesn't, you don't have to try 10 times or 20 or more to make it work.
Right. So I think from our experience, since now we are learning features which is relatively small than the raw pixels. So from our experience, for the features, it's quite easy to generate. Also, we have this distillation loss during the continual learning, and we can actually keep the generator to generate quite good features for all the classes we have seen. But when we try to go down, to generate some features with large number of feature maps, then in that case it doesn't work well. We couldn't make its training well.
Okay, that would have been my follow-up question, because you showed that in one case, in the 25 tasks,
Yeah.
Like you struggled a bit more, and that would, from your numbers, would suggest, because your generator and discriminator are really small, basically.
Yes.
That you could just use bigger ones, basically, and that would help. But what you just said is like, then it's where it gets hard, basically.
Yeah, if you want to generate some like more complex features, it could be harder.
Okay.
Then of course, like if you have maybe a bit larger generator, it could be helpful also in that case.
I see. Okay, so you think you would have to kind of make them match in a way, at least in terms of dimensionality or expressive power, or however you want to frame that.
Right. Yeah. Yeah.
Cool. Thank you.
Thanks.
Hi, guys. One question.
Hi.
Thanks for the presentation again. So I'm not sure, maybe you covered it, but do you have any numbers how better is feature replay than sample replay? Generated feature replay versus sample replay, generated sample replay?
Yes, in the paper we have shown the comparison between the image generation on CIFAR-100 and feature generation on CIFAR-100, and we, from our experiments, like using this feature generation is much better, since like when you try to do the CIFAR, like you want to do the generation on CIFAR-100, like the generated images are not that good already. So we couldn't like really get the better quality images. Then if you go to ImageNet, let's say, then I guess you have problem to generate the images. So that's why we did show indeed show some comparison, like of course if you go like to some tiny data set like MNIST or CIFAR-10, in that case, you might get better performance by using image generation. But when you want to go to like more realistic, larger data sets, then we would say it's better to generate features.
Yeah. Do you think that on the feature level, you might have less forgetting, let's say, because, you know, features are like more abstract than just concrete samples? Is it like part of your hypothesis, maybe?
Well,
I'm not sure if it makes sense, but you know what I mean?
Yeah. So in principle, like if you can generate images, I think that's always good, because you can train the whole model end to end, right? It's perfect. But when you cannot generate really good images, then you want to go to some like simple version, which like we choose to generate the features on the top of feature extractor. And we have seen like some people try to generate some features in between. I think that could be perfect, but in the end, from our experience, it's really hard to generate like the feature maps in the middle layer of the networks.
Thanks.
Yeah.
Yeah, if I can add something to this question, I mean, I understand the reasons on why you want to work on a, let's say, latent space in the network, especially in terms of efficiency, right? Because you're saving a lot of memory, and I mean, generating features is quite easy when you have a trained generative model, so it's all good. But I want to ask, what do you think about, you know, instead of keeping samples from the input space, like instead we did keeping samples in the feature latent space instead of generating one. For example, in your setting, since you're working in the second last, let's say, layer, so the latent space is fairly small, right?
Right.
So in that case, you could also save a number of examples, a number of features, from the examples from the past, instead of generating them, and you would not have like a big overhead in terms of memory nor computation, because you're not computing more than because you're not generating samples. So have you thought about these? What are your ideas on why it's better to generate samples, especially that high in the latent space, and instead of keeping just examples like standard inertial methods, but not in the sample, of course, not in the input space, but in the space.
Yeah, I think what you are saying make total sense. You could, for example, from practical sense, you could just keep some like features if you assume your feature extractor are not changing too much. Yeah, I think that could be another like comparison to do. We haven't done that. But yeah, it's very interesting to keep also the features, because the features again have like relative small memory usage, right? That's what you mean.
Yeah.
Yeah. We didn't try that, but that's I think in practice it's also another good way to just reduce the memory. Yeah, you are right.
Yeah, I mean, our hope in trying to do this as well, we are working on generative feature replace somehow.
Right.
Is that if you can generate features, maybe you can generate even hallucinate new things that you have never encountered before. So theoretically, if you have a very good generative model, you can do better than just keeping old features. You can generate them on the fly, the number that you want, and you can maybe mix things that make sense together to improve your recognition capability in this case.
Hey, yeah, you are right, because we start using this generative feature replay. Actually, we get some insight from zero shot learning. So in that case, actually, when you have some semantic space, then you can actually generate some categories like you have never seen. So in that case, maybe generative models still like have some better compared to only the raw features.
Yeah,
you are right.
Any more questions? All right, so let's thank our speakers for today. Thank you very much, Sailei and Cheng-Sen, for joining us today. Please, once I create the topic on our forum, please send your slides if you can, so that the other can find these, and maybe also link to your paper and additional material that you want to share.
Okay,
and
great.
Thank you all again for joining, and see you to the next reading group session next Friday.
Okay.
Bye.
Bye.
Thank you. Bye.
Thank you. Bye.
Yes. Thank you for the nice talk.
Thanks.
Thank you.